In section 9.10, we're going to talk about diffusion and osmosis, terminal speed, and how the terminal speed can be affected depending on whether you're doing sedimentation, which is controlled by gravity, or centrifugation, which is when you put something in a centrifuge. In the diffusion process, molecules move from a region where their concentration is high to a region where their concentration is lower. And here's an example. Uh, you've got a low concentration of a substance and a high concentration of a substance. You suddenly remove the barrier between the two, and in general, the particles over here will move into this region. We have an equation for this process called Fick's law, and it basically goes the amount of mass going through the barrier over a given time is equal to the diffusion rate. I'm going to do a cursive D for that, times the area of the, let's say we've got an area between two uh, regions, and it's kind of bad. I drew that three-dimensionally, but I drew those one-dimensionally, but that's okay. Um, the diffusion rate times the area divided by the length. So this is the length here. And then we'll have concentration 2 minus concentration 1. We'll have C2 and C1 would be in kilograms per meter cubed, probably, like the mass per unit volume of the, is it? Yes, they're measured in kilograms per unit per cubic meter. So that is interesting. It's got the same units as density, but since density usually is the whole amount of a substance, this is just a part of the amount of the gas or fluid that is sitting there. And then we already divided by the length. Okay, so there aren't any examples in this chapter, but I did write down number 73 is a use of Fick's law. So let's look at number 73. It says sucrose is allowed to diffuse along a 10 centimeter length of tubing filled with water. So that means L equals 0.10 meters. The tube is 6 centimeters squared in cross-sectional area. So that means the area is 6.0 centimeters squared, and I'm going to go ahead and convert that in line. Centimeters per meter, 100 squared. So that will be 6 times 10 to the negative fourth square meters. They went ahead and gave us the diffusion coefficient. Let's see, diffusion coefficient is 5.0 times 10 to the negative 10th meters squared per second. And it says 8 times 10 to the negative 14th kilograms, so that's probably part of a concentration. Actually, no, that's a mass. Delta M equals 8.0 times 10 to the negative 14th kilograms. It's transported along the tube in 15 seconds. So finally, delta T equals 15 seconds. What is the difference in concentration levels of sucrose at the ends of the tube? So we'll just solve this equation here for delta C. So it'll be L over dA delta M over delta T, and that's it, I think. And the answer came out to be 1.77 times 10 to the negative third kilograms per meter cubed. If you look at this table, you can see we had the diffusion rate of 5 times 10 to the negative 10th meters squared per second was given in the problem. But if you weren't given the thing, and you were given that it was oxygen through air, oxygen through tissue, oxygen through water, etc., you could use this table. It does include 5 times 10 to the negative 10th. Multiply that by about 100,000, and you get the rate, the diffusion coefficient of oxygen through air. That's much, much faster. And take the same number and divide it by about 1,000, and you get the diffusion coefficient of hemoglobin through water, which is much, much slower. In number 74, you'll notice that it says the concentration gradient is 3 times 10 to the negative second kilograms per meter to the fourth. So the change in concentration right here is kilograms per meter cubed, and then divide that by L, and you get kilograms per meter to the fourth. So this is equal to the change in concentration divided by L is what that value is that they're giving. The next topic in this section is about the size of cells, and in particular, the surface area to volume ratio. This kind of seems like a coincidence, but all three of these shapes have the same surface area to volume ratio. For the cube, the surface area is 6L squared because there are 6 sides and each side has area L squared. The volume is just L cubed. So if you divide L squared by L cubed, you get 6 over L as your surface area to volume ratio. The sphere has a surface area of 4 pi r squared, and its volume is 4/3 pi r cubed. Dividing out the 4, dividing out the pi, you get 3 r squared over r cubed is 3 over r, and r is half of d, so you get 6 over d. 6 over r is half of L, so you get 6 over L. And this one, the let's figure out the area of this part. It is 6 pi r, no, 4, yeah, 2, wait a second, 2 pi r. 2 pi r would be the radius around, and the height is L, or 2r, divided by plus pi r squared, divided by the volume, which is pi r squared times 2r, the area of the surface divided by times that. One last thing, there's a 2 here because we got the cap up here and the cap down here. And so this is 2 times 2 is 4 pi r squared plus 2 pi r squared over 2 pi r cubed. 2 pi r cubed. So what do we get? 3 pi r squared over pi r cubed, which comes out to be 6 over L. Now there are odd shapes that don't have a surface area over volume of 6 over L. It's just that these are a good approximation for symmetrical bodies. So if you are about 1 meter tall and you just kind of use this as an approximation to your surface area divided by your height, L equals 1 meter, then your surface area over your height would be 6 per meter. Sorry, surface area over volume would be 6 meters cubed per meter squared, or 6 per meter. If you are uh, an ant that is 0.001 meter long, then your surface area over your volume is 6,000 per meter, 6,000 meters cubed per meter. Oops, I didn't have it on the camera. Okay, you 6 per meter, an ant 6,000 per meter. How about a cell? Let's say we've got a blood cell which has uh, say 6 micrometers across. Then 6 divided by 6 times 10 to the negative 6th comes out to be 1 times 10 to the 6th meters cubed per meter squared. Or, I mean, sorry, meter squared per meter cubed. It's got just a massive surface to area, surface to volume ratio. So I want to try to plug that into the diffusion rate somehow. They seem like they don't finish the discussion in the text. Okay, to finish their description, I'm going to take this equation and try to plug it into this equation. So what I've got is surface area over volume equals 6 over L. And I am going to change that to 6 over 2R to represent the radius of the cell. So that is 3 over R. And the reason I want to change it to an R is because in equation 9.7, we got delta M over delta T equals dA. And I'll just write delta C over L, the change in concentration. And the L down here was the length, was the distance. Like if you had a cell like this, the L was the length of this, basically the width of the cell wall, while R is the distance from the center of the cell to the outside. So I don't want to use the same variable for both of those. Now I'm going to basically just replace A, diffusion rate, this is the surface area of the entire cell, so it's going to be 3V over R times delta C over L. And I'm going to replace delta M with a density times a volume, which in this case is the current concentration times the change in volume. And that's going to be divided by delta T. And I'm going to modify this a little bit more. So I want the proportional change in volume over delta T over here. And so we'll have the diffusion rate times 3V over R L times the proportional change in concentration. And this V shouldn't be here. And so it's delta C over C. And okay, so now we can see that the proportional change in volume will go up greatly if the radius of this guy is, say, 6 micrometers, then that is 6 times 10 to the negative 6. And then if L is, say, even uh, 1 1 1 1/10 1/100th of that, 0.06 micrometers, that will make this even less. So if you have a very small radius and a very small width there, it would mean that your change in volume of the cell, it'll shrink or expand. Now they've got a couple of examples of this. For instance, they have a particular cell in the body has a sugar concentration of 1%, and so it's got a 99% concentration of water. And then it's placed in a concentration of 5% sugar and 95% water. Now, the cell wall doesn't let sugar pass through, but water does. So what happens is the water comes out and the cell shrinks. Then they talk about the behavior when you got a 9% sodium chloride salt solution versus a 1% sodium chloride or salt solution. And saline is what they say. So in a 91% case, the water comes out and the cell shrinks. And in the 1% case, the 99% water outside is greater than the concentration in the cell, and water goes in, and the cell may burst.